Our speaker today is Mel Shochet. He's the Kirsten Distinguished Service Professor of Physics at the University of Chicago. For those of you that don't know academic jargon, a Distinguished Service Professor is kind of the top of the food chain at the university. We invited Mel because of his research interests, which involve the interactions of elementary particles at the highest man-made energies. I'm not going to try to describe his actual research, but I tell you a little bit about his background. He began his work in this area in the late 1970s as part of a team that formed in 1976 to work with the collider detector at Fermilab to search for the top quark. 76, he told me that that project ended last year. So he's been at it for a while. In 2006, he was appointed as the inaugural chair of the High Energy Physics Advisory Panel, which provides the Department of Energy and the National Science Foundation with recommendations on the U.S. national program in experimental and theoretical high-energy physics research. And last year, as part of the ATLAS team that involves 3,000 scientists from around the world, they were responsible for one of the two large Hadron Collider experiments involved in the discovery of the particle that is consistent with the Higgs boson. And so please join me in welcoming Mel Shochet.
Thank you. So when I was asked for a title of the talk, I suggested the Higgs boson. If not the God particle, then what? Well, the title didn't quite wind up that way, but let me take just a minute to get rid of the God particle part, and then I'll spend most of the time talking about the Higgs boson. Many in our field bemoan the title of that book. Leon Lederman, Nobel laureate and longtime director of Fermilab, wrote a popular book about particle physics, about the research, and part of the discussion there was the search for the Higgs boson. And the fact that it is so difficult to find, at that point, no one knew whether it existed or not. But in order to either find it or refute its existence, it was an enormous challenge. And Lederman, in his typical style, referred to it as that goddamn particle. The editor at the publishing house picked up on that and said, that's the way we'll sell books. We'll call the book The God Particle. And that's the way it happened. So beware of editors. Okay, so what I want to do this morning, it's challenging, and that is to tell you what the Higgs boson is and why it's needed to describe the universe about us. It's hard because it inherently involves the quantum mechanical nature of the universe. And when we hear about anything in any field, we try to use our intuition to understand whether it makes sense to try to picture what it might be. And the problem is that the quantum mechanical nature of the universe is really only seen in the microworld, in molecules and atoms and scale smaller than that. So it's nothing that we're accustomed to when we grow up. Our five senses don't give us access to that world, and so anything of a quantum mechanical nature is not intuitive to us. It doesn't seem sensible. And so that's part of my challenge this morning of trying to place this into a picture that is understandable. I have to start with the role of symmetry in physics. It has been one of maybe the most powerful tools that we've had to go from experimental observation to a theoretical description, a description of the universe that's broader than the specific observations that we've made. And so I have to tell you a little bit about that, how that works, because the Higgs boson and the reason for its existence involves a symmetry principle, and fortunately or unfortunately, a quantum mechanical one. So it's one layer further down in depth. So let me start with the role of symmetry in physics. So for that, we have to go back to Emmy Noether, who was born in 1882 and died in 1935. Einstein called her the most important woman in the history of mathematics. She had all the problems of women in science in the early part of the 20th century, whether it was here in the US or in Europe. She was in Germany. So for example, for 7 years when she was doing extraordinary mathematical work, she had to work as a volunteer with no pay because women didn't get academic appointments at that time. And in 1933, when the Nazi government dismissed all Jews from academic positions, she was forced out. She came to the United States and went to Bryn Mawr College outside of Philadelphia, but unfortunately, just a few years later, she died of ovarian cancer. She's had many contributions to mathematics, but her contributions to physics is what's called Noether's theorem. And let me first tell you what it is, and then I'll try to explain what the words mean. It says that if the laws of nature possess some symmetry, then there is a corresponding conserved quantity. So what the heck is a symmetry and what the heck is a conserved quantity? I think the best way to explain that is to give you some examples. So in the 17th century, it became clear that momentum is conserved. Momentum is the mass times the velocity of any object. And if you have objects colliding, it was observed that the momentum before they collided would be the same as the net momentum afterwards. Newton put it in this way: a body in motion remains in motion, and that's essentially a statement of conservation of momentum. It was also understood at about the same time that energy is conserved. It can't be created and it can't be destroyed. It can change from one form of energy to another, but it doesn't disappear. Descartes and Leibniz talked about that. With Noether's theorem from the mathematics, what can be shown is something that's quite interesting, and that is that the law of conservation of momentum, the fact that a body in motion remains in motion, can be derived directly from the observation or the assumption that the laws of nature are the same here as in California as in outer space. In technical terms, the laws of physics are invariant to a translation, to moving from one place to another. Newton's law, F force equals mass times acceleration, is just as true on the moon as it is here. It doesn't matter where you are. Similarly, the law of conservation of energy can be derived as a direct consequence of the observation that the laws of nature are the same now as they were last week, as they'll be 100 years from now. Again, in technical terms, the laws of nature are invariant to a translation in time. It doesn't depend when you do an experiment. The laws that govern the experiment will be the same. Let me give you one final example of conservation law and an invariance, a symmetry related to it, because this will be somewhat related to how I describe the Higgs. And that's something that you may remember from school called conservation of angular momentum. Angular momentum is a rotational version of momentum. It's essentially how much rotation some object has. So you can imagine a drum major with a baton flipping it in the air and it's spinning. When it's spinning, it has angular momentum. That conservation of angular momentum that says the spinning momentum of an object is conserved. It's the same now as it will be later. And that's a direct consequence of another observed symmetry in nature, and that is that the laws of physics. For example, F equals ma is the same whether I'm pointing in this direction or heading in this direction or heading in this direction. If I set up an experiment on the table with a ball rolling down an inclined plane, the result of that experiment will be no different than if I rotate the table and do it again now where the plane is pointing north rather than east. And that the fact that the laws of physics are the same no matter what direction you're pointing is what we call rotational invariance. And from that, you can prove that there is conservation of angular momentum. But now an important distinction, and one which we'll play back with the Higgs boson, and that is that what you prove is that the laws of nature possess this symmetry. They must be the same no matter what direction your experiment is pointed. But it doesn't say that the objects involved in that experiment have to be the same in all directions. And an obvious example is that drum major's baton. It may be the fact that the laws of gravity and the laws of motion are the same no matter what direction you're pointed, but that baton isn't the same in all directions. It's got one direction that's very long and two directions which are very thin. That's just the shape of a baton. So the object that the laws apply to don't have to possess that symmetry. That's not required. Okay, so the Higgs boson, what is its relation to symmetry? Well, to tell you where it fits into what we call the standard model of elementary particle physics, and the standard model tries to describe in the simplest terms possible what the building blocks of the universe are, what everything is made of, and how they interact. They interact so that those building blocks can form this table, for example, and it sticks together. There are forces that act on those particles. So in the standard model, matter is composed of a small number of building blocks. There are the quarks, which make up the protons and neutrons in atomic nuclei, and they're the leptons, like the electrons that orbit about the nucleus to make up the atoms. And these building blocks, these constituents of matter, are held together by a small number of forces. We know of four forces in nature. There's gravity, there's electromagnetism, and then there are two forces which only act within the nucleus, what we call the strong nuclear force, which holds the protons together and keep the electric repulsive force from blowing all of nuclei apart, and then the weak nuclear force, which is responsible for radioactive decay. The force between two objects, and then they start to get into this strange quantum mechanical nature. So you have two objects. How is the force transmitted from one to another? So very likely in junior high school, when you were studying electricity, there were a couple of pith balls that were hanging from strings, and you put electric charge on, and you saw that if it were the same charge, these pith balls would repel, and if one was positive and one was negative, they would attract one another. How does this pith ball know that the other one's there and know that it should move away? In the quantum mechanical picture that we understand of the micro world, what happens is that a quantum, a particle that carries that force, is interchanged back and forth between these objects, and that's how each one knows the other one's there. Sort of like a couple of kids throwing a baseball back and forth. Even if it got dark, as long as they could feel that ball hit their glove, they would know that the other one is there. So that's the picture that we have for how two objects interact and feel forces between them. And the standard model is essentially a single equation that describes the interaction of all of the elementary particles in nature. This standard model has correctly predicted the outcome of thousands of experiments that we've done over the last 40 years. It was derived and it was proposed in the 60s based on a symmetry argument. Now, it isn't easy for me to describe that symmetry argument because, as I said, it's inherently quantum mechanical, but I'll try. What it's related to is the phase of a wave. What's the phase of a wave? Well, if you think of a water wave, there are peaks of the wave and then there are troughs of the wave, and there's somewhere in between. And the phase just tells you whether you're at a peak or whether you're at a trough or whether you're halfway in between. And it's the statement that the laws of physics are the same even if you were to change the phase of the wave a different amount at every point in space. It's a strange symmetry. As I say, it's really not anything that we have intuition with because it only acts in the quantum world. So why do you think there is such a symmetry? And the reason is that when this symmetry was proposed, the description of the forces of nature and the elementary particles that came out of that assumption agreed extraordinarily well with every experiment that had been done up until then and every experiment that's been done since then. And these phase symmetry arguments, there's some direct consequences that we know about. So one direct consequence of one of these phase symmetry arguments is the conservation of electric charge. So if you have these two pith balls and they're both charged positive and you bring them together and let them touch each other, in the end you still wind up with pith balls with positive charge on it. The charge doesn't disappear. But if you take two pith balls, one positively charged and one negatively charged with the same amount of charge, and you bring them into contact, after that you wind up with no net charge, because plus and minus, when you add them together, if they're the same amount, can neutralize one another and you get zero. So there's a conservation of charge, which is a direct consequence of one of these phase symmetry arguments. Okay, so what does this have to do with the Higgs boson? And the answer is that the simplest application of the symmetry, of this phase symmetry, provides a theory that although in many, many ways, as I said, gives you just the structure that we see of the universe, there were two things that were severe problems that you couldn't get away with. One is that with that phase symmetry, the strength of two of the forces, the electromagnetism, which is responsible for radio and television and so on, the strength of that force and the strength of the weak nuclear force that's responsible for radioactive decays had to be the same. Yet they were observed to be far from the same. The weak nuclear force is 1 billion times weaker than electromagnetism. Moreover, with this phase symmetry, you could prove that there could none of the building blocks of nature, none of the quarks, none of the leptons, none of those force carriers could have any rest mass. So what's rest mass? Well, E equals mc squared. Mass is just a form of energy. We know objects have energy. They can have energy of motion, kinetic energy, if they're moving very fast. They can have potential energy, energy due to forces with other objects. You take a bowling ball and you move it halfway up a hill, and it has gravitational potential energy. We know that because if we release that ball, it accelerates and rolls down the hill and increases in velocity, and that energy of the force between the Earth and this ball gets converted into energy of motion, into kinetic energy as the bowling ball spins up. What's rest mass? Rest mass says that one of these building blocks, an object that we think is not composed of anything, it is elementary, that even if it's at rest, no energy of motion, even if it is far away from any other object, no potential energy, no energy due to forces, that it would still have energy. That's the rest mass. And this very nice standard model based on the phase symmetry said no particles could have rest mass. We know of some like that. The photon, the quantum of light that carries electromagnetism, has no rest mass. But most of the building blocks do. The electron has a rest mass. In fact, if the electron had no rest mass, no atoms would be stable. There would be no atoms, no molecules, and no us. The universe would consist of electrons and protons flying around at the speed of light, and the universe would be filled with light, but there would be no stable matter, nothing like this table. So these predictions of this symmetry-based theory were just clearly wrong. There was a problem. And here is where Peter Higgs and several others come into the picture. They introduced what we call dynamical symmetry breaking. And what they did essentially was they introduced one more force field, which we call the Higgs field, whose quantum, whose particle that carries it, we call the Higgs boson. And they produced a situation that's analogous to my drum major's baton. So they said, yes, the laws of physics have this phase invariance, but what they're applied to, the universe that we see around us, does not. Just like there was this invariance to how I'm pointed, but the baton itself was not a spherical object. It had a long direction and it had two small directions. So with this addition, it was possible to have a picture in which the weak force was much weaker than electromagnetism, and in which the building blocks of nature had rest mass, and the electron and nuclei could actually form stable atoms. But this Higgs field, in its quantum mechanical structure, was unlike anything anybody had seen in nature, anything that had been observed. And so, although you take it seriously, because with it now, literally all observations that we had made could be explained by this standard model, including the masses of the various objects. So you take it seriously and you try to experimentally verify whether it's true or not. You don't know that it's true. Maybe there is some other explanation that is correct. So it's the old philosophy, trust but verify. And so that's been our job for a long time. So what does this Higgs field do? Through its interaction with the elementary particles, it provides the mass, the rest mass of those particles. And because there's a Higgs field permeating the universe, all of the building blocks get their masses. So I use an analogy. I don't think it's a great analogy, but I think it makes the point. Think of a platoon of soldiers marching across a field. They can move at a pretty fast clip. And now imagine at the end of the field, they come to a region which is this thick in mud. It's really hard to march fast when your legs are this deep in mud. So because it takes enormous energy to move, they slow down, and it's really hard for them to speed up. So they naturally have a great difficulty. They have to put enormous energy to speed up. Well, how much energy you have to put to accelerate, to increase your speed, is in fact just what we mean by mass. If you see a stroller on the sidewalk, it's pretty easy to start pushing it down the sidewalk. If you see an SUV sitting in the street, it's not so easy to push the SUV down the street, and that's because it's much more massive, and it takes an enormous amount of energy to change its speed from 0 even to a half a mile an hour. And so the Higgs field serves the analogous role of the mud. It just makes it difficult for things to be moved to have their speed increase as you go through this Higgs field. So there is a possible solution. The laws of nature maintain this phase symmetry, and thus the agreement with all of our experiments can be understood, but we pay a price for it. The claimed existence of a new force that we've never seen, a new force field that exists everywhere. Well, for those of you who have learned something about the history of physics, this might sound very familiar. It's a bit like the luminiferous ether. The luminiferous ether was proposed more than a century ago to explain, in quotes, what it was that light waves traveled through. It had been discovered that light was a wave-like phenomenon. You could have, it could be bent in lenses, for example. You could have interference properties. So it was known that it was a wave-like property, but every wave that people had observed traveled through something. There was a medium. Water waves, the water went up and down, but it was traveling through water. You could have a wave on a string, but it was the string that was carrying the wave. Sound waves were understood to be carried by the air. If you had an evacuated chamber, the sound did not propagate from one end to the other. And so, by analogy, they said, there must be something that's carrying the light waves. And they didn't know what it was, so they made up luminiferous ether, which was later disproved when the careful measurements of the speed of light were made, and then Einstein's theory of relativity came in. But there's a big difference between the luminiferous ether and the Higgs field. And part of the difference is in our understanding of nature, because we now understand that in the quantum mechanical world, in the micro world, the vacuum is not the absence of everything. In fact, it's a seething cauldron with objects popping in and out of existence very, very quickly. And so it is possible that there are Higgs bosons that are popping in and out of existence. But still, trust but verify. So it's just a hypothesis, this picture, unless we can experimentally observe the Higgs field. So how can we do that? Well, as I said earlier, the quantum of the Higgs field is the Higgs boson. If we can produce the Higgs boson and detect it, and its properties are just the properties predicted for such an object, then we'll have some evidence that we're on the right path. But we have to do that, and that's been the challenge for a very long time. How do we produce it? Again, it comes from E equals mc squared. If we can get enough energy in a small enough volume, that E, that energy, can be converted into mass, into that mc squared, and you can produce new massive objects like the Higgs boson. And that's just what the big particle colliders do. The Tevatron at Fermilab, which operated until last year, now the Large Hadron Collider at CERN. They accelerate protons up to almost the speed of light, very close to the speed of light, enormous energy, have them collide head-on, and you have this great deal of energy in a volume that's smaller than the size of a proton. And out of that energy density, you can produce new objects. That's how we produced the top quark that we discovered at Fermilab about 15 years ago. So there are two problems if you want to discover the Higgs boson this way, by colliding these particles. And that is that the standard model predicts lots of properties of the Higgs boson, but not its rest mass. And so I have no idea what the rest mass of this object was. And the fact that the Higgs boson interacts very weakly with the building blocks in nature. Because it produces the rest mass of objects, it actually interacts with objects in proportion to its rest mass, which means that it interacts quite strongly with the top quark, but you don't find the top quark in a proton. The constituents of these protons that are being collided at CERN or at Fermilab, those quarks are the lightest quarks. They're the ones that interact most weakly with the Higgs boson. And so the problem is that even if you get all of that energy in a small volume, it is very, very, very rare that you would produce a Higgs boson. So that is part of the experimental challenge, not knowing the mass and the fact that you have to have trillions and trillions of collisions to have the hope of producing one of these. So the search for the Higgs boson started soon after it was proposed over 40 years ago. as accelerators became more and more energetic, higher and higher Higgs masses could be searched for because you'd have more energy in this little volume and produce higher mass objects in principle from E equals mc squared. Yet until this year, none was seen. And in fact, we had gotten to the point where almost all possible masses of the Higgs boson had been ruled out for those masses which would still give consistency to the standard model, still render it a reasonable description of nature. There was just a very narrow window left. And fortunately, that is where we did find the Higgs boson, with a mass of approximately 135 times the mass of a proton. So let me finish then in just a few minutes and tell you how we saw it. The Higgs, like most of the particles we study, is metastable. It decomposes almost as soon as it's produced. What we observe are what it decays into, and then try to reconstruct, try to infer what it was that was produced. One of the ways that the Higgs boson decays is into two photons, two quanta of light. There are lots of things that produce two quanta of light. A good example is in a PET scan. A radioactive material is injected into the body. It's material which tends to go to particular organs. And that radioactive material, when that radioactive decay occurs, produces two photons, two quanta of light, which are detected by the PET scan equipment. And because there are two of them and they're back to back, you can extrapolate back and find out where in the body that radioactive decay occurred, and therefore where that material was had migrated to. So here we have a Higgs boson that can decay into two photons. The signature of a particle of definite mass, like a Higgs boson, that decays into two photons is that the sum of the energies of the two photons you detect will just be mc squared, the mass of the parent particle, in this case the Higgs boson. Now there are lots of processes in these collisions that produce pairs of photons. So how do you distinguish it? Well, for all of the other processes, the sum of the energies of the two photons are all over the place. So it's a continuum. Any sum of energies is possible. So if you plot the number of these photon pairs that you see as a function of the sum of energies, I don't know whether you'll be able to see this, but the details aren't important. You just get a continuous distribution. You get a lot at some energies, a little less at others, but at every sum of energies you get some number of these objects. That's an indication that you haven't seen a new particle of definite mass. If you see a new particle of definite mass, superimposed on these pairs of photons of all energies will be a peak in which the sum of the energies of the two photons always give you the same number, and that's the mc squared of the new object. And so that's what you look for. If you can see, there's a little bump here, but if we try to look at the excess, it's down here, and you see, if it's not too far for you to see, that there is a bump in the data just at that point, and this is where the energy, the mc squared of the Higgs boson. We didn't just see it in pairs of photons. The Higgs boson could also decay into not only pairs of the carrier of electromagnetism, but pairs of the carrier of the weak nuclear force, the so-called W and Z bosons, and we saw pairs of those, again, with constant sum of energy at the same energy as the pairs of photons. And the ratios of how many we saw into pairs of weak force carriers versus pairs of photons was just what was predicted by the standard model. But maybe we're fooling ourselves. Maybe we wanted to see that, and so we saw it. Okay, so there a little bit of the sociology. So these experimental collaborations are enormous. There are two major ones at the CERN Collider in Geneva, Switzerland. the one that my group works on, the Atlas experiment, and then there's the other one which the group at Northwestern works on, which is the CMS experiment. Each one of these collaborations contains about 3,000 physicists. These detectors that we built are enormous. They're about the size of 5-story buildings. They contain millions of individual particle detectors designed, built, maintained by the physicists in the collaboration. And each one of these experiments, they're of very general nature. So there are hundreds of different important scientific questions that you can probe with the data that we collect. And that's why you can have so many people working on it. You break down into small groups, as small as 2 or 3, as big as 30 or 40, to focus on a particular scientific question. So they're small groups within this giant collaboration. But in any case, there were these 2 collaborations. They work independently, and they work secretively until their results are published. So we did not know what the CMS collaboration was finding, and they didn't know what we were finding. At the public CERN seminar this past 4th of July, the 2 experiments presented their results on the Higgs boson. The spokespeople of the 2 experiments did that. Each of the experiments presented their results and then asked one question: what's the probability that we're fooling ourselves and it's just a random occurrence? You can flip a coin 10 times and you can expect on average that it'll land 5 times heads and 5 times tails, but sometimes it'll be 7 and 3, and in very rare occasions it could even be 10 heads and no tails. Maybe we were just fooling ourselves. So you do a very careful statistical analysis, and each experiment calculated that the probability that what was seen was just a statistical fluctuation was less than 1 in a million. So you have 2 groups, didn't know what the other one had until the seminars were given that morning, each finding that there was evidence for a new object with a probability of 1,000,000 to 1 that it wasn't just a random occurrence. And then the final conclusive piece of evidence is that the masses that these 2 experiments found were exactly the same. So it's not like one found a mass at 135 times the mass of the proton and the other one at 160 times the mass of the proton. They agreed to within 1% of each other, which was the accuracy of the measurement. So that, in fact, convinced us, that along with the fact that the properties measured so far of this object looks very much like what had been expected for the Higgs boson, that we had indeed discovered the last missing piece of the standard model of particle physics. With that, I will stop.